And so it's time for another simulation video. This time we're going to use simulation to understand the chi-square goodness of fit test. So it's a simulation, so I'm going to use a computer language, but remember these videos are not about the computer language. It's just about understanding what we are doing with these simulations, just to show how good these theoretical models that we have, in this instance the chi-square distribution, how useful they are by just doing simulations. So we're going to do a hypothesis test for chi-square goodness of fit. And we're also going to do some bootstrap confidence intervals in this video. So the file will be available in a link down in the description. But remember, again, it's not about the code. It's about understanding the simulation and how that fits in with what we do when we use a chi-square goodness of fit test. And so here's our Jupyter notebook, understanding the chi-square goodness of fit test using simulation. So our Monte Carlo methods, and then a bootstrap for our confidence intervals. They are the packages in Julia that I'm going to use. I'm just going to say it once again. Remember, this is not about the code, but of course, this file will be available to you if you want to play with the code. So let's look at our research question. It says a city's health department has historically found that among individuals who received a seasonal influenza vaccine, 30% obtained it in a pharmacy, 50% at a primary care physician's office, and 20% at a community health clinic. So determine if this distribution has changed recently. Maybe something happened in that county or in that state, and you need to test whether these proportions under the null hypothesis still hold true. They select a random sample of 300 vaccinated individuals, and they were surveyed regarding where they received their vaccination. So if we can state these proportions under the null hypothesis, that's what I've done for you in this table. And I've just put the subscripts pharmacy, physician, and clinic, and we can see under the null hypothesis, we think that the population proportions are 0.3, 0.5, 0.2, which is completely fine. They sum to 1 or 100%, which is what we want. And so what we're going to do now is I'm just going to use my computer, and I'm just going to generate 300 random observations using this distribution of proportions, 0.3, 0.5, 0.2. That's exactly what I've done. If you want to have a look at the code, I'm just creating a variable called n. That's my sample size, and I'm setting that to 300. There's my sample space, physician, pharmacy, and clinic. There's my proportions, 0.5, 0.3, 0.2. And then I'm telling my computer, well, just generate 300 random values, observations, using those proportions. And this is what my computer came up with. If you run the code, you're going to get exactly the same results. If you seed the pseudo-random number generator with the number 42, that means that the pseudo-random values that we're going to get will look exactly the same for everyone. And then I use this count map function on my 300 observations, and I find, and this is just simulating me doing my study once, going to these 300 individuals and surveying them, and it seems like 52 received their vaccination from a clinic, 147 at a physician, and 101 at a pharmacy. And now I'm just going to divide each one of those by 300 so that I can have the proportions. So in my case, I see 17 and a third percent received it from a clinic, 49% from a physician, and 33 and 2/3 from a pharmacy. And so there we have our proportion estimates. These are the sample proportions, 17%, 49, and about 34%, just rounding. And so if I want to visualize this, have a look at this. In blue, we see our expected proportions, 20%, 30%, 50%. And in this reddish-orange color, we see the observed proportions. And what the chi-square goodness of fit is going to do is just to say, can we express how different it is from what we observe is from what we expect? And if I look at this bar chart, this paired bar chart, I can tell you now it's probably not going to be that much different. It seems like that this is a good fit. So instead of using a mathematical model, in other words, a probability density function for some distribution, which will be the chi-square distribution, of course, on 2 degrees of freedom, because I have 3 categories and 3 minus 1 is 2, let's just use simulations. Just to use this goodness of fit, chi-square goodness of fit test to get a solution to our question, do the observed frequencies differ from the expected frequencies? So what I can really get my computer to do is to say, create for me 300 random observations, calculate the frequency of each, but do this 100,000 times. I've just chosen 100,000 here. You can do 200,000, 300,000. Computers these days, of course, can do many of these calculations, no problem. I'm just going to do 100,000 for the sake of this video tutorial. And but what I want you to imagine is you waking up 100,000 days in a row, and every day you are going to observe values for 300 subjects. Just simulating this fact that we're doing the study over and over again. And I'm using those same proportions under the null hypothesis. So what we are telling ourselves when we are doing this frequentist approach to statistics in hypothesis testing is that imagine that the null hypothesis is true. I have those three proportions. If that was true, and I would repeatedly sample 300 observations or individuals then from their population, and I do this over and over again, 100,000 times over, what would the distribution of these proportions look like? And that's exactly what I've done here. I'm just saying, create these samples for me, do that 100,000 times over. There's my repeat there, 100,000 times. So I'm taking 300, and it's going to generate for me those 300 observations from those proportions under the null hypothesis for these three categories. And I'm going to do it 100,000 times over. Let's look at the first one of these 100,000. There you can see them. In the first one, my frequencies were 68, 139, 93. Of course, that was different from what we simulated imagining that we had done our study once. And so I want to just save all those values, and I'm just showing you the first 5 here. So these are just the values of each one of these. So if I look at that first of the 100,000 simulations, there we go, 68, 139, 93. My next simulation ran and it was 59, 142, 99. So this is me doing my study 100,000 times over. I just want to now look at the values that I would expect under the null hypothesis. Of course, if I have 300 observations and I say that 20% of them should be the clinic, then I would expect 60. If 50%, I would expect 150, and 30%, I would expect 90. So now I can use my equation here for my x squared statistic. I'm just going to sum over the difference between the observed and expected value squared divided by the expected value, and I do that for one of each of the categories. So if I just go back here, just to show you, so in this first case, there's my first of my 100,000. So for that one, it's going to be 68 minus 60 squared divided by 60, then 139 minus, there's 150 squared divided by 150, and then 93 I should say minus 90 squared divided by 90. And then if I sum over all those, I get an x squared statistic. And then I go to my second run, and then the third, until I go through all 100,000 so that I have 100,000 x squared statistics. And now I wonder, if I create a histogram of these 100,000 x squared statistics, what would that look like? What would that look like? Now, on a computer, to generate a histogram of 100,000 data points is a bit much, so I'm just randomly selecting a couple of them and plotting them on the screen, and just look at this beautiful plot that we have here. Here's a histogram of all my x squared statistics, and I've overlaid for you in orange, there's our mathematical model, probability density function of the chi-square distribution on 2 degrees of freedom. And look how beautifully our data fits this theoretical model. And this is just using simulation, just showing you this beauty of these models and how we can use them in our hypothesis testing. But yeah, I'm not using it in my hypothesis testing, I'm purely simulating data. But just look at that beautiful approximation that we do have there. So I can do this and look for critical value. Now, one thing I can do is let me take my 100,000 x squared statistics, and I can simply calculate the 95th percentile. So if I calculate the 95th percentile of all those 100,000 x squared values, I'm saying which of those x squared values would only have 5% of the values more than that value. And that's exactly what we do in hypothesis testing for an alpha value of 0.05, isn't it? So if I do that, I get a value of 6.004. So I'm saying from my 100,000 x squared values, the 95th percentile value is 6.004. So 95% of those x squareds will be less than 6, and only 5% of them will be more than 6. So in my plot, that's going to be around about there. So we're saying there is my critical value, and my region of rejection will be those 5% least probable values in that upper tail. Now look, if I do this from my theoretical model and I say, let's use the chi-square distribution on 2 degrees of freedom and calculate the 95th percentile for that, I get 5.99. Look how close that is, 6.00, 5.99. That's very, very close, and that's only doing 100,000 simulations. The more you do, and then in the limit go to doing it an infinite number of times, these values just get closer and closer together. Just showing us how good this model is of the chi-square distribution on 2 degrees of freedom and how well that fits our data. But I could just simulate that, this Monte Carlo simulations. I did it 100,000 times over, looked at all those x squareds, and just look how well that is. So let's calculate the x squared statistic for our data. Remember, we had, when we just did that simulation the first time, we had 52 people from getting the vaccinations at a clinic, 147 at a physician, and 101 at a pharmacy. So there's my expected values. Remember, those would be 60, 150, 90 under the null hypothesis. And there I do my x squared statistic. 52 minus 60 squared over 60, plus 147 minus 150 squared over 150, 101 minus 90 squared over 90. So observed minus expected squared divided by expected. And my x squared statistic is 2.47. And once again, remember, my critical value was at 6. And now I get a value here around 2. So clearly I am in this region of the 95% most common x squared values, definitely not in the region of rejection, which is the 5% least probable x squared values, right in the upper tail. So we're going to say, well, we failed to reject the null hypothesis in this instance that we had. So I hope that showed you how we can use simulation and just, look at it visually and see how close this is to these theoretical models that we use when we do hypothesis testing. So I hope that gave you a good indication of that. Now, what we would also like to do is just use simulation to look at the confidence intervals around these sample proportions that we found. And so what we're going to do is use the method of the bootstrap, or the bootstrap method. And now what that says is the following. I have 300 observations. I'm just thinking about that doing my study once. If those 300 individuals were selected without bias from the population, I can assume that they are representative of the population. And now why don't I use them as a surrogate for my population? And from those 300 values, I am going to randomly select 300 values. Well, you might just say, well, isn't that just the same values? And I'll say, no, we do a special kind of selection. We do selection with replacement. So imagine I put those 300 values in a hat, all each individually on a piece of paper. So I'll have I'll have 52 that say clinic. I'll have 147 pieces of paper that say physician and 101 that say pharmacy. And I put them in a hat. Now I'm going to randomly select one from the hat, write it down, but then I take that piece of paper and I put it back in the hat. So it's available for reselection. So I'm making up the situation where those 300 values are a surrogate for my population. And so I'm imagining that there are many more than just 300 in there. And I do that by just replacement. Every time I select one, I throw it back, which means if I do this, some of them are going to be reselected and some of those pieces of paper are never going to be selected if I do 300 with replacement. And that's exactly what we do with the bootstrap method. So what I'm doing here is I'm saying, take those 300 pieces of paper, put them in a hat, the 300 from my initial study. Let me select at random, one by one, 300 of those, every time putting it back in the hat. And I do that over and over again. So I'm going to do that, and I'm going to calculate the frequency for each, and I'm going to do this 100,000 times over again. And again, 100,000 times is nothing. I can do this many, many more times over. And again, I'm just simulating this over and over again. This time around, you can look at the code. I've saved it as a data frame object. So you can just look at these proportions. Now there'll be 100,000 of these rows in the first resampling with replacement. I had for the clinic 22 and 2/3, 22.67%, 46.3%, and 31% for the pharmacy. The next time around, 19.7%, 47.3%, 33%, etc., etc., etc. Over and over and over again. And now what I can do for the clinic, for all the 100,000 clinic values, let me work out the 2.5th percentile and the 97.5th percentile. In other words, I'm capturing the middle 95% of all those values. So for the 2.5th percentile, 2.5 percentile, I would get only 2.5% of those values. Those clinic proportions would be less than that value. And if I look at the 97.5 percentile, only 2.5% of values would be more than that. So I'm capturing this middle 95%. Now, this distribution of these proportions are not normal, so I'm not going to get symmetric around my observed proportions. And that's what I've done for all three of these. So look at that. For the clinic, our sample proportion was 17%, but we get a 95% confidence intervals using those quantiles of 15.67%, or around about 16% then to around about 25%. As you can see, it's not symmetric around the 17 like we have with symmetric distributions. And for the physician, we had a proportion of 49%, and we work out a 95% confidence interval of 0.44 to 0.56. And for pharmacy, we had 0.34, 95% confidence interval of 0.25, 0.35. And in all three of those cases, we'll see that the proportion under the null hypothesis is indeed within each one of those three confidence intervals. And that also just supports the fact that we failed to reject the null hypothesis. So what I'm doing with these percentiles, remember, I'm taking all these 100,000 values in the clinic column, all those proportions in the clinic column, putting them all in ascending order, and I'm calculating the value at the 2.5 percentile value and the 97.5 fifth percentile value, so that I capture the 95% most common values in the middle. Great stuff. So we've used the simulation and here the bootstrap method to think about the critical value, see where our statistic fell in amongst all those possible values that the test statistic could take under the null hypothesis, and then we use bootstrap resampling just to look at the confidence intervals for each one of those proportions.